All right. So today we are going to be creating a piecewise function and graphing a piecewise function using transformations. Write the piecewise function associated with these graphs. So taking a look at graph number 1, looks like we have a quadratic and a linear, and those two together create the graph of f of x. If you remember what a piecewise function is, a piecewise function is a function that is defined by multiple functions over a given domain. So this function is defined by, it looks like, two functions of quadratic linear over different domains. So the quadratic function, the domain seems to be as long as x is less than or equal to 1, because the filled in circle, and the linear is where x is greater than 1 because the open circle. So let's create the equations of these. So if we're taking a look at our quadratic, it appears that our vertex, which is normally at 0, 0, got shifted down to -2. But it looks like our pattern is still the same: up 1, right 1, left 1, up 3, left 1, up 5, left 1, which is a normal x squared quadratic. So it's just a quadratic that is shifted down 2. So our first equation is x squared minus 2, as long as x is less than or equal to 2. And then our linear equation looks like it has a slope of 1 and a y-intercept of +1. So we get x plus 1 as long as x is, that is not correct. That should say 1, not 2. 1. And 1. All right, so there's example 1. Example 2, it looks like we have 1 over x, and we have a horizontal line, y equals 2. 1 over x is over the domain from 0 to 2 inclusive. So as long as x is less than or equal to 2, again, because the filled in circle. And we have y is equal to 2 as long as x is greater than 2, because not filled in circle. So we end up getting 1 over x as long as x is less than or equal to 2, and 2 as long as x is greater than 2. Our next graph appears to be a quadratic and an absolute value. So the vertex of our quadratic looks like it got shifted left 2 and up 8. And taking a look here, it does not appear that there's any sort of vertical stretch. We still have that down 1, right 1, down 3, right 1 pattern, right left 1 pattern of a normal x squared, but there is a reflection over the x-axis, so we know that our a value is -1. So as long as our domain is between -4 inclusive and 2 non-inclusive, because the open circle, so -4 is less than or equal to x, which is less than 2. We end up getting that quadratic with the a value -1. And that should be a +2, because it got shifted left 2, not right 2. And +8, very good. Between -4 inclusive on the -4 and non-inclusive on the 2. Good. And then our other one is absolute value. Again, our vertex got shifted to the right 6 and up 3. And our slope appears to not have changed. It's still down 1, right 1, down 1, right 1, down 1, left 1, down 1, left 1, but there is a reflection again over the x-axis. So we put that all together, and our domain is from 3 inclusive to 9 non-inclusive. So we end up getting negative absolute value of x minus 6, and then plus 3 between 3, which is less than or equal to x, which is less than 9. All right, our next graph appears to be a linear with a cubic. So our linear function has a slope, it looks like, of down 1, right 2, so negative 1/2 with a y-intercept of 2. So we have the equation y equals negative 1/2 x plus 2 as long as negative 4 is less than x, which is less than or equal to 2. And then our cubic function, it looks like the critical point got shifted to the right 3. So our C value is 3, but it does not appear to have any other shift. We still have the right 1, down 1, left 1. Oh, I'm sorry, I apologize. Yes, there is a shift because normally it's x cubed is 1 cubed is 1. So normally we're like this. So there is a reflection. So we could actually make that a reflection over the x or the y-axis. I like to leave it as a reflection over the x-axis because then you don't have to worry about a b value other than 1. So we put that all together, and that's between 2, which is less than or equal to x, which is less than 5. Now, actually, I said 2 is less than or equal to x. You can choose where you want to pull that equal sign. So I actually had the equal to here for the linear, but you could have instead included it here and then had less than 2. The reason why is that point is on both of those graphs, both of those functions. So as long as it's included on one of them, it's included for the graph as a whole, but it doesn't matter which one because it's technically could be on either. All right. Number 5, we have an absolute value and a square root function. If you're looking at me and you're like, how do you know those so quickly? Because I know my parent functions. You have to know your parent functions. Again, those parent functions are linear, quadratic, square root, cubic, cube root, absolute value, and rational. All right, so number 5, we have absolute value, and again, vertex was shifted here, left 2 and down 2. But it looks like our slope is still 1/1. So it's the only shift we have here. So we have absolute value between -8, which is less than x, which is less than or equal to 2. And again, we have here for, come on, the 2, you can, since it's on both graphs, you can actually attach it to either function. I chose to attach it to the absolute value, but you could attach it to the function we're about to do, the square root function. So our square root function, our critical point got shifted to the right 2 and up 2. And let's see, it doesn't appear that anything else has changed. Yeah, we're still good. So just a shift, no reflection, no translation, or no vertical or horizontal stretch or shrink. So we have that square root function between 2, which is less than x, which is less than or equal to 9. So again, square root of x minus 2, and then plus 2 between 2 is less than x, which is less than or equal to 9. But you could have taken that equal sign and instead attached it there if you would prefer. All right, number 6, we have x cubed and then what looks like a quadratic. So x cubed, normally critical points at 0, 0, but it got shifted to the right 1. And this graph looks like there's a stretch, but the scaling is just, look at the way the x-axis is scaled compared to the y-axis. That's why it looks all stretched. So we're still going right one, up one, left one, down one. So there's actually no vertical or horizontal stretch here. So just a shift to the right one. So -1 is less than or equal to x, which is less than 3 for our x cubed. So we get the quantity x minus 1 cubed between -1, which is less than or equal to x, which is less than 3. And then for the quadratic, our vertex got shifted to the right 5 and up 4. And let's see, it's still, yeah, that's 4. So our pattern is still up 1, right 1, up 1, 2, 3, right 1. So again, no vertical or horizontal stretch, just the translations. So we end up getting the domain of that 3 is less than x, which is less than 7. So we end up getting the quantity x minus 5 squared plus 4 between 3, which is less than x, which is less than 7. All right, let's do a word problem. Number 7. A wholesale store sells paper plates for $3.27 per package, up to and including 15 packages purchased. If a customer buys more than 50 packages, the price of the entire package drops to $2.73 per package. Write a piecewise function for this pricing structure and determine the price a deli owner would pay for 75 package plates. All right, so we have 2 scenarios here. We have when it's price per package up to and including 50 and then over 50. So wholesale sells paper plates for $3.27 per package up to and including 50. So that means that f of x is equal to 3.27x when x is between 0 and 50, inclusive on both ends. So 0 is less than or equal to x, which is less than or equal to 50. But when x is greater than 50, then f of x is equal to 2.73x. Because it's for the whole thing. So you don't have to worry about buying 50 at this price and then the remaining few at a different price. The whole price drops down to that amount. So that's our piecewise function for this scenario. So B, price for 75 packages. So since x equals 75 is in this domain, that is the function that we will end up using. So 2.73 times 75, so we end up getting a total of $204.75. All right, number 8. Is this function continuous at the points where it is pieced together? So if you're wondering what continuous means, let's look at our previous graphs. For example, graph number 1, not continuous because there's that gap in our range. Number 2, not continuous because there's that graph in our range or gap in our range. Number 3, not continuous because we actually have a gap in our domain and our range. But if you look at 4, we have continuous because one function flows right into the next function. There's no gap in the domain and range when the 2 functions piece together. And it was the same thing for number 5. So, wrong direction. All right, so is this function continuous at the point where it's pieced together? So we need to check at the points where it is pieced together. So that would be at 0 and then again at 3. So looking at where x is equal to 0, that is piecing together, I should use a highlighter, x plus 1 and 2x plus 1. So substituting 0 into those 2 functions, we end up getting that the 2 functions end up equaling 1 when x is 0, so it will be continuous at x equals 0. Now, looking at where x is equal to 3, that's piecing together the 2x plus 1 and the 4 minus x squared. So we test the point x equals 3 into those 2 functions. and we end up getting the 2x plus 1 is equal to 7 when x is 3. And 4 minus x squared is equal to negative 5 when x equals 3, so it is not continuous at x equals 3. Number 9, find the value of k that makes the following, let me move this, function continuous. So that means that when these are pieced together, so at x equals 3, we want these two function values to equal each other. So that means that we want 3 plus k, because again, x is 3, equal to 2 times 3 squared. So we end up getting k to be 15. All right, number 10. The fish population in thousands in a lake at any time x in years is modeled by the following function. This function describes the sudden change of the population in time x equals 6 due to a chemical spill. Don't know what just happened. Sketch a graph of the piecewise function. So we have 2 to the x between 0 and 6. Really quickly, just create a quick table from 0 to 6. So that's 2 to the 0th, which is 1, 2 to the 6th, which is 64. So we have 0, 1, 6, 64, and we know the shape of 2 to the x. And then 4x plus 8, as long as x is greater than 6. So that's, let's see, when x is equal to 6, we have 6 times 4 plus 8, so that's 32. And then we have a positive slope of 4x. So we get our graph looking like that for the second function. Open circle here because it's not equal. X is not equal to 6. It's just greater than. So that's our starting point and everything above. All right, so B, describe the continuity of the function. So since the two functions do not have the same y value at the same x value, x equals 6, that point of piecing the two functions together, it is not continuous at x equals 6. How many fish were killed by the chemical spill? So chemical spilled at time x equals 6. So at that time, it appears that it dropped from 64,000 to 32,000. So that's 32,000 fish lost. Because again, remember x or y is fish population in thousands. And then D. At what time did the population recover to the level it was before? So we want to know when is that second equation equal to 64,000. So we have 64 equals 4x plus 8, 56 equals 4x, x equals 14. So it took 14 total years, so that means 8 years after the chemical spill. All right, and then our last example, graphing piecewise functions. In order to graph piecewise functions, you can use transformations, you can use a table, it's kind of up to you. I personally use transformations because these are all pretty basic transformations. So we have the horizontal line, y equals 6, as long as x is less than -7. And then we have the square root of x, which was shifted to the left 7. So that's between -7 and 3. So we have our function there. And open circle at -3. And then we have the absolute value function that was shifted to the right 2, down 6, and then scaled vertical stretch of 2. So we shift that to the right 2, down 6, and then we go up 2, right 1, up 2, right 1, up 2, left 1, up 2, left 1, over the domain -3 to -4, inclusive on both ends. And then we have x cubed that was shifted to the right 6, between, as long as x is greater than 4. So open circle where x is equal to 4, arrow on the other end, so keep going. And if you're not quite there yet with transformations, you can always do this the long way with a table of values. So like, for example, if we're doing 2 times the absolute value of x minus 2 minus 6, we have between -3 and -4. So -3, -2, -1, 0, 1, 2, 3, 4, etc. Plug those points in. So -3 minus 2, -5, absolute value is +5, times 2 is 10, minus 6 is 4. So we have -3, 4, etc. Keep plugging them in, plot your points over the given domain. All right, so that is the conclusion of today's lesson. I hope you found it informative. Go ahead and give tonight's homework a try. If you have any questions, please join me for office hours. All right, so in the meantime, please stay safe, stay sane, and please, 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 please stay distant. Bye.